Okay, today we're going to talk about terminal velocity. So up to now, we have mostly been ignoring air resistance as a force. The reason for that is simple. It's because for the most part, most problems, it doesn't play a big role in the problem of and figuring out the net force. And the reason that is because the velocity of the object is too small to generate really any noticeable air resistance. So today we're going to start looking at one particular situation in which that's not the case, in which something is traveling at a very large velocity and there will be a very significant amount of air resistance. So at this point, I need you to pause the video and I need you to read all of the intro. And then I need you to click on this link and watch this video about air resistance, about skydivers. Once you've done that, come on back and we will fill in the free body diagrams below. Okay, hopefully you enjoyed the video and the reading. Now we're going to go ahead and we're going to draw some free body diagrams. And the first one we're going to draw is for an object that is accelerating downward with a very small air resistance. So here is the object. I can get my pen working. And we're going to do our free body diagram like we always do. The first question we're going to ask is, what is the non-contact force? And of course, if the object is falling or if it's a person, that was the worst straight line ever, we know we're going to have a force of gravity acting down, okay? Now in this case, we're assuming that the object is moving, but it's moving slow enough so that the air resistance is very small. Now, we're going to go ahead and put an air resistance going up. We know it's up because if the object is going down, the air resistance is always in that direction opposite to the motion, so we know the air resistance has to be pointing up. In the second case, we have a similar situation, same person, so we have the same force of gravity. That was a little bit of a better arrow going down, but now we have a larger air resistance, so the object has spent a little more time falling, and the air resistance has grown. It's not quite as large as the force due to gravity yet, but it's bigger than it was. So that's our new free body diagram. And then in this third box, we finally have a situation now where the force of air resistance is so large that it actually equals the force of gravity. So again, we've still got the force of gravity going down, has not changed. And now we've got an air resistance force going up, and it is exactly the same size as the force of gravity. We call this terminal velocity. The reason it's terminal is because it's the last velocity that the object can have unless something changes. Now, the problem, of course, as we saw in the video, is that if nothing changed, that terminal velocity is really, really fast. And if that person were to hit the ground at that speed, well, let's just say it doesn't end well. So that's why we're going to go ahead and we're going to have this person deploy a parachute. Right? When they do this, now they've greatly increased the force of air resistance acting on them. The force of gravity hasn't changed at all, but now we've got this huge force of air resistance pushing up. So let's think about this in terms and context with our kinematics knowledge. We can see now that the net force is going up, right? It's pointing up. So that means then that the acceleration of this object is also up, right? So it's up. It's not, the arrow doesn't mean increasing, it just means that it's pointing up. Well, if the velocity is pointed down and the acceleration is up, we know that this object must be, or this person must be getting slower. That's the whole point of the parachute, right? We want this person to get slower. We don't want them to go splat when they hit the ground. Now, let's talk about how the parachute increases the air resistance, okay? We know the parachute increases the air resistance because the parachute will increase the cross-sectional area of the skydiver. And when the cross-sectional area increases, when we have a larger area, we know that the air resistance force will increase. Okay, so a bigger cross-sectional area, bigger resistance, air resistance, okay? Now, how can we tell when an object reaches terminal velocity by looking at a free body diagram? Well, if the force of gravity down is equal to the force of air resistance up, we know that the acceleration has to be zero, right? We can see that the net force is zero, the acceleration must be zero, the velocity is constant. That's the definition of terminal velocity. Okay? Real short notes today, only, what do we got here? 5 minutes. So if you have any questions, you can ask in class. Take care.